So this is the important result. You can read this thesis of frequency available online at Caltech. Self-assembly of linear duplex DNA into linear polymers produces several languages for finite parameter. Self-assembly of duplexes, hairpin special kind of structure. I'm not showing today. 3-arm junctions produces context-free languages. And self-assembly of double cross molecules, which I showed, they achieve universality. So this is a really powerful thing. By just changing the DNA hardware, you can do all kind of computations, right? With the DNA now, you can do computation. Now I will show you some basic arithmetic how you will do with DNA, addition, subtraction, those kind of things. Okay. In fact, a lot of literature is available. Basically, finite field arithmetic people have done pathfinding, Boolean stability problem, fast Fourier transform, NTRU, triple system. A lot of arithmetic are already being developed. So you can actually, whatever area you are interested, you can actually contribute here, right? In terms of designing those tiles actually for doing this. I'll actually talk about binary counter as a toy problem, how it is done. So we want to create this pattern. So you see these are the binary numbers. So these are the numbers like 0, 1, 2 in the binary expansions are right there. We want to create this counter. Okay. We are assuming infinite counter right now. Okay. Can we create this? How many tiles are required? And how do we do this using this tile assembly model? So actually, if you look at here, there are only, and these are, so there are 2 colors used here, 0, 1 at the edge, and here actually whatever is here, we have written here. So sorry, whatever is here, we have written here. Okay, the top. Can actually actually 4 is optimal, you will see. But I'll show you now how to find out this solution. That is a tricky thing. And so actually, if you are trying to find this solution, you are doing DNA computer. So you can call yourself as a programmer for DNA computer, because now you have to design this solution set. Okay, these tiles. Now there, by the way, you don't have to worry. Our group has developed a software which can do this for you, easily. But it's really a nice thing. Let me show you. So these are edges are known as pad, and you can think there is some relationship here in input-output. Output 1 here is XOR of input 1 and input 2, and output 2 is AND of input 1 and input 2. And this is how these numbers will be computed actually. Okay, so 2 sides are input, 2 sides are output. Okay, and with this computation, now you see how it can create this. So these are the 4 computational tiles. Seed tile you require. You see seed is here. Okay, and then that is the starting tile. Then this vertical frame tile will attach here, horizontal frame, and then once this is done, this is value is 0, this is 1. So basically from here, only this tile can come, right? Because the color matches. Temperature of the system is 2, okay, and strength of each corner is 1. So it measures the system temperature, and these things will combine. So essentially, the whole pattern can be created. So question is, can I do better? And sometimes there are errors also. I'll show you some more solutions. You see, this is same binary counter, but now 8 number of tiles are used. Okay, same binary counter. So question is, in fact, there was an open problem that we solved at that point of time. Can we, because what happens when we increase number of colors or number of tiles, errors can be reduced. Actually, this is thermodynamic process. When you really build this in the system, actually, it will grow, and because of errors, there may be problems because tile may have mismatch, or there is a partial hybridization between ACGT at the corners, right? So that will create a problem. So to overcome that, we introduce more basically more colors here, and that reduces the colors actually. That's really very basic thing. So let me show you. This is the 8 color solution that I have written by hand, and this was the open problem after that. And it was solved by both Wilfie and myself and my collaborator Naveen, who is at IC now. So I have given only a sample of this is a 16 color system. So now we have any two power to. Okay.
You are saying you have increased the number of tiles to reduce the error.
Yeah, yes. So basically, the same problem can be solved with different kind of tile solutions are possible. That's what I want to show you, right? This is the. And this is for Sopranski triangle actually. This is a tile system for that actually. Okay. In fact, you can design these tiles. We have developed the software, and where you can actually enter the things and you can actually create the tiles. It will generate the tiles, for you. And now I'll show you the addition for 8. This is by Brun. So if A, B, and so we take input as a binary numbers like this, and you see these are here, okay? And these 8 ties will combine and give you the output here, 1 0 0 1 1. Okay, A plus B. So this is a unidirectional solution. That is also possible, right? So essentially, problem is how do you find these solutions? That is a mathematical challenge, right? For any given problem, you need to find these ties. I'll show you some of these.
We have a mathematical vindication of the existence of such tilings.
Yeah. In fact, there is I would say about 100-page paper is there. It's old paper. Yeah. So that's what Winfrey, has looked at it, and then he designed these things here. Okay. Now this is 16 color solution. I'll show you how addition is done. You see, X and Y. So on one edge we have X, okay, 1 0 0 1, and then 1 0 1 0 1 0. On this side is Y. And addition. Now addition you can take anywhere. You can actually, here it is in diagonal. You see diagonal is 1 0 0 1 1, which is the addition. Okay. So you can design these sides. And now solution is in the diagonal. If you want, it can be on the upper corner or whatever corner, right? So those things are in your hand, depending on how you design the tiles. Okay. So similarly, we have the subtraction. I'll not discuss too much, but subtraction can be done. Multiplication, another solution. Division, division is there. All these things have been implemented, right? So with tiles, you can do all the basic arithmetic. By the way, you don't have to do anything by hand. We have the software right now available, which you can use at StyleMod. And actually, you can just give what you want for any expression. It will give you the tile set automatically. Okay, so that we have done. And then you can simulate it on this XGrow software. Okay, so you can actually see the simulation before doing the experiment. Okay, so this is some simulation pictures. Okay, now I will talk about chemical computing. Chemistry is a beautiful thing. Again, Winfrey in 2007 showed that bunch of chemical reactions can simulate an equilibrium. So basically, you can do computation with chemical reactions as well. I will show you a simple example of multiplication. How to do multiplication with chemical reactions. So programming the biochemistry. So basically, again, we have analogy. Right now with our computer, high-level computer, assembly board, assembler, machine code, and hardware. Now in the DNA system, there is a work compiler by another group actually. Then we have the reactions in terms of biochemistry. Winfrey group has developed DNA assembler, which will give you in terms of DSD, known as dynamic strand displacement. So essentially, what is that? Bunch of DNA strands, they dance and fight with each other and implement the computation actually for you. Beautiful thing actually. And the key idea about DNA computation is the hybridization. DNA hybridization is the backbone. Okay. So let me show you this example of multiplying two numbers. So this is a pseudocode for multiplication. Now these 4 reactions can implement multiplication. Okay, you see how. 4 reactions, and you see there are rates: slowest, fastest, fast, and slow. Okay, 5 means null, means it's going into it's vanishing. So these 4 reactions, how it will implement? Let us take an example. Okay, we have 2 and 3. We want to multiply 2 and 3. So we take 2 molecules of X and 3 molecules of Y, and final output I want in Z. Okay, Z variable. Now these reactions will fire. So first, as soon as the value X is 2, 1 molecule of X will be taken, initialized, and the first reaction will fire, and one catalyst is created. Okay, so here it is. You see. So that means now X is decreased by 1, and 1 molecule of I is created, right? Yeah. Now that's first reaction. Now what will happen? Now the second reaction. As soon as catalyst is present, this reaction will fire immediately. And that means 1 molecule of Y will produce 1 molecule of Y prime and 1 molecule of Z. Right? So 1 molecule of Y prime and 1 molecule of Z.
What is at the second line on the right hand side? Y to the index.
Which one?
Third from no, this one on this side.
This side.
Yeah, second equation. Yeah.
Second, I plus Y prime plus Z.
Y?
Y prime.
Y prime.
Yeah. Or you can call Y dash, whatever. Just a variable. So X is going to I is a catalyst. As soon as catalyst is there, 1 molecule of Y is giving one molecule of Y prime and one molecule of Z, right? That is this one. Okay. Next reaction will do. You see, second time, because now again another molecule is there, right? Y. So it will consume that Y, and now you see the count has increased, right? Second reaction is fired. So 3 times second reaction is fired. Then now catalyst is not needed. So that goes to 5. So I goes to 0. So now the total configuration is 1, 0, 0, 3, 3. So X is one molecule of X now, Y is 0, and 3 molecules of Y prime and 3 molecules of Z. Now again, because X is 1, again it will start the loop from the first, right? So, by the way, here in between Y prime molecules, we convert into Y because we need Y also for the multiplication, right? So whatever is temporary variable Y prime we are using. So this will give us 3 times this reaction will fire. So 3 molecules of Y prime will convert into 3 molecules of Y. Okay. Now again the first reaction will fire, and then everything will repeat.
Determine 3 times or 1 time, how many times you
Yeah, I have written this number with how many times it is running.
How do you determine that 3 times? Why do you have to
So that's so basically very yeah. So actually the question is how do you control this? It's all this get by choosing these rates. Okay, you need to have synchronization among the reactions, right? So that you can control everything. So it's a beautiful thing. Okay, so people have actually done tremendous different kind of mathematics using this. All you whatever you want to do. We have actually done. Prime determination we have done with these so many kind of things. You can do all the mathematical problems you take and see if you can design these chemical reactions. You see, everything is open. Whatever interests to you in mathematics. So finally, again, this I goes to 0. So we have the six things, right? 6. So Z is 6, right? So this is how you implement multiplication. You will find there is a paper programming the biochemistry where you find exponentiation, multiplication, different things.
Final result here.
6. 6 molecules of Z.
Okay. But I mean, I'm just doing loud thinking.
Uh-huh.
Aren't we killing a monster with a bullet? Literally? I mean, what do we achieve this? Because there's a lot of competition involved in getting 6 by multiplying 2 to 3. That we can do far more simply.
True, that is true. But basically, one thing is that in terms of so you are asking what is the use of doing these things?
Because I mean, do we save computational?
There are some work in terms of the computational complexity when you use calculation. But the purpose of this chemical computing is a bit different actually. Okay, it's all chemistry.
But then, I mean, are we saving time?
No, you are saying very correctly. That is these are the things started in 1994, and we are not having that kind of the pace in DNA computing as in other fields, right?
Or you can make it
And
more
that is
efficient.
only because of this, we have the complexity in the simple task. Like, as we are seeing that, the multiplication of just 2 and 3, so many things are there. Okay. And so the complex, when we increase the complexity of big problems, some little bit higher computation, the complexity is the main.
Yeah. Correct.
This might perhaps facilitate that.
This is basically not facilitating the researcher.
That's what I'm saying.
Yeah, so because that is the problem. Because you will not find the many literature, even currently, I don't think a lot of research work is being on the DNA computing.
No, actually, that's not correct. Actually, I should want to make you
In some particular area.
the application is different. Okay, what I'm saying that we are not using for the normal calculations what you are trying to do here, right? The application is different. For example, this field combined with DNA origami has produced a vaccine.
That may be different.
Okay, so different kind of applications are there. The domain is totally different.
When
So these computers will not be used for actually calculating. This is a toy.
Yes,
Toy
but
example.
what you are saying is an example, but I mean, along
Yeah.
these lines, you could perhaps.
You can probably do many things.
Yes, it can be beneficial for the
People have done even the logic gate and circuits they have built. Everything can be done. Okay, so now I'll show you some news headlines. I think. See, DNA computers can play this game. They have done the experimental demonstration. So tic-tac-go game. Origami, as I mentioned, this field has. This is by Paul Rotman, who was one of the collaborators with Winfield. So they have created these maps of world and these smiley faces. So actually, you are getting control of DNA in designing whatever you want at 2D level. Later on, it was expanded to 3D level. So 3D origami is also created. Okay, this is the DNA origami counter. Okay, DNA walker. You can robot is created. Then actually scale to measure distance at the nanoscale that has been created using DNA. Okay. Then square root calculator using DNA. This is done by Winfrey Group. Okay. AI. So artificial neural network has been implemented in DNA strands. This is the code from Winfrey. At last, we have a small test tube of over 100 of DNA strands playing games with you, trying to use the mind acting like a lovely tiny brain. So 2011 they have done this. Okay. Shapes you can create. In fact, we have developed the software which can do this easily now. Skin computing has emerged in 2012. Xylem computing, again, the whole book, and a lot of things have been done, especially from circuit design and many other things. Wi-Fi has come rather than Wi-Fi. This is biological internet. Bacterial hard disk, so you can store data in bacteria. We have done this experiment. We have stored data in bacteria and retrieved it successfully in India, actually. Then there are other bacterial computers that have been developed. I'm just showing the snapshot because in 35 minutes I cannot discuss all these things. By the way, this Mona Lisa image processing was done by Lulu Kwan, the wife of Eric Winfrey. In fact, she got motivated by our work on image that we have done, DNA Image Pro. I'll show you some of our basic thing. The DNA storage is one area. So 1 gram of DNA can store 455 exabytes of data. So 2 gram of DNA can store entire internet. And right now there are commercial companies which are developing Catalog, spin-off of MIT. They are developing this machine to store data into the DNA. There are another company in Europe, BioMemory. They are developing this tool, and we are contributing even in the JPEG, the image that you take from JPEG, JPG. So that is standard for DNA. They have developed. I have contributed there actually also ISO. Okay. So here we have done the demonstration to the Prime Minister by storing data into the DNA. This is 2018 January. We have our software Backsoft for storing data into the bacteria. You can use this software to storing data into bacteria. This is the image that we have stored. This is the book that is first commercial DNA-based book has been released. Okay. We have these 14 software products that I was mentioning, different for different tasks. Okay. So I don't have time to discuss all of this, but you can find. I'll give you one or two. You see, using our software, you can create this. We have created the map of Gujarat using DNA. This is so we have written OM here. You see the map of India. This is the way you see. When you create this OM, backend these DNA strands have been created, output of the software, and they combine. Okay, they sort of combine each other to form this shape at the nanoscale. Okay, 3D DNA software is there, which okay, sorry. So DNA Image Pro, you can actually do image processing with DNA. Ultimately you can do anything, whatever you want. This is again we have a software. Finally, I just want to mention that we have one of our books is coming on DNA data storage. The first book actually on this topic. It will be coming in January or February from Stigma. And there are, as I mentioned, for DNA Kelsey, we have written one book. I have to submit to the publisher. Another one on chemical computing. All these are first time, these books have been written actually on these topics. And thanks to my collaborators and funding bodies. These are my students, okay, who have contributed. And I think Steve Jobs' statement that in 21st century, there's a lot of interaction between, biology and computer science. So you can, tremendous opportunities. Thanks. If you have any question. Yeah.
I have a simple question. We showed DNA thing so that the computations can be done. My question is, does it give an insight on how, let's say, we do computation, let's say? Of course, we manipulate humans.
So, by the way, I have not shown those slides, but the Lozer Penrose and Stuart Hamrock, they have given a model of that inside our brain. We have there's a protein called tubulin, and that can be in two states, alpha and beta, and that actually qubit. So there is a quantum computer sitting there. So that's why we have the consciousness. that model has been described, yeah. So,
But there's also animals and things like that. When they also do some calculations from
Yeah,
something or
so,
something like that. I'm just trying to say
yeah,
that.
yeah. So I think
how the nature.
people are trying to, so basically, you see, for example, if in plants, right, different things. So there is the computer science, we have these 4 machines, right? So the production rules are linear. Like one, then another, right? But if you do the parallel production, so you can actually do what is known as L systems. And then there is a book known as Algorithmic Botany. It describes a lot of beautiful things about plants and everything. In fact, Steve Jobs used that in his company Pixar for creating artificial forest and everything. Using those algorithms. So how to actually, because see, when you are looking at a plant, so there's a systematic pattern, right? So it has to go a certain distance, then there is another branch, right? Or then there is a flower. It's very systematic. So there are rules which can create this kind of thing. That book, Algorithmic Botany, describes all those things. There's also another book, Algorithmic Seashell. All these books are available. I mean, you can read, whatever is there. I have given only very small 2 examples, 5 examples, and on the internet, there's a whole course available which you can do. I mean, look at. We have taught this course for 5-6 times on DA computing.
Any other questions? Well, if not, that's fine.
I don't mind time, right?
5 minutes चल जाता है
Huh?
5 मिनट चल जाता है
Okay.
3 मिनट चलाया नहीं। इन्होंने चलाया नहीं।
That time
मेरे को आप चला के दिखाइए
कुछ रहते हैं इसलिए वही तो
30+5 लिया था। 30+5 नहीं किया।
वैसा फिर आप ही मेरा टाइम रख लीजिए बिकॉज माय वॉच इज स्लीपिंग
मैं वापस नहीं करूँगा। क्योंकि बेकार है। ठीक है। Well, now we have the second speaker, well known, Professor Tofi from Kashmir University. And in fact, a very good friend of mine. We keep pulling each other. You must have already seen this. Please, go ahead.
Well, begin by thanking the organizers, Pankaj Mishra, Pankaj Mathur Saab. I don't know why for inviting me into this conference. I mean, it has been a regular feature over the last several years, and I always love coming back and some old friends and make some new friends. But I'm going to talk about an issue which is, quite familiar in the entire mathematics community. I'm not going to add extra wisdom to what most of you would already be knowing. To put things into perspective, I mean, you must have noticed a common thread in all the talks that have happened this afternoon, this morning. What's that? I mean, you may have different points of view to look at it, but I mean, as I see it, the problems they all start off with, starting with Balasubramanian. The problems are easy to state, the problem is, this simple innocent looking problem about the existence of some few sets. That's on an integers, no abstract structures more or less, right? And then about substract algebra. So then it was vector algebra and its applications, and finally, again, a very familiar concept of curvature. And then, to begin with, these were all elementary topics, but as they went down the line, it turned out that a lot of complicated mathematics was involved. I'm supposed to take a departure from that. I mean, the topic is familiar, very elementary at that, but and the proof of the main statement that's going to motivate the discussion is very, very elementary, a two-line proof about the existence of non-measurable sets. But my mission here is to make things complicated. I'm going to make use of very non-trivial techniques, some complicated mathematics to prove the existence of non-measurable sets. Why do I do that? The students, could they tell me? Why should I choose to be a masochist, self-inflicting pain, who am someone who relishes this thing? Why should I do it? I mean, something that I can do in a line, and I'm devoting something like 10, 15 pages to a proof of that. Why would one do that? I mean, what could be
Is there in your title?
huh?
Is there in your title? You want to do it without axiom of choice?
So here it is. Actually, every statement in mathematics, every theorem in mathematics which makes use of the axiom of choice, it motivates the question whether axiom of choice can be dispensed with. So that's a natural question, and that has been bothering mathematicians for a long period of time. Somewhere they have succeeded, but elsewhere they haven't. Like in the first course in master's course in topology, you learn the Tishnov product theorem, right? It makes use of the axiom of choice. And in an effort to prove the same theorem without axiom of choice turns out to be futile because two are equivalent, as we know. Now, so far as non-measurable sets is concerned, it's a very complicated situation, a very awkward situation. Sets of real numbers which are supposed to have a good property, which happens across the board, but then there are sets which don't have that property. So it's a very irritating thing. And axiom of choice tells us that there are non-measurable sets. So the question is, how do we get rid of it? Well, how was I motivated to get into this? Had other reasons. I'm not a logician by training or someone who's an expert in the foundational principles of mathematics to bother so much about the axiom of choice. Actually, I ran into this issue for very different reasons. You see, over a period of time, I have been interested in the issue of extending maps, morphisms from a category of objects, which could be Banach spaces, Hilbert spaces, Fréchet spaces, Wigner spaces, topological spaces, or matrix spaces. And then there are different kinds of morphisms. When can I guarantee? When do I guarantee that? So, in other words, given an object, a mathematical structure, a mathematical object, right? Whatever it is, it could be a group, a ring, a field, or whatever. And you take a part of it, subgroup, subfield, subring, and you have a homomorphism sitting on it, on that part of it, subset, subring, or subgroup. Can you extend it to a homomorphism on the big group, on the big ring? So this is the generic question, right? So this is the same question. I mean, you can put it in the framework of category theory. You have an object and a morphism depend on the sub-object of that object, whether it can be extended to a global morphism. Extended means it retains its original values on that part of it. So the story begins with linear maps in Banach spaces. That's my first interest. And then one lands into a different territory, involving vector metric spaces. But on metric space, you don't have a linear structure, so you cannot talk about linear maps. So what we talk instead is of Lipschitz maps or isometries. Can we, if we are given an isometry, means a map which preserves the distances, can I extend it to a global isometry on the big object? Or if you have a Lipschitz map, it's a non-expensive map, master students must know it.
with a K on the right hand side, which could be greater than 1. If it is equal to 1, you get a non-extension map or a contraction. So, this further led to consideration of what is called the extension of measures. Given a measure defined on a on a part of a sigma algebra, whether you can extend it to a measure on the entire sigma algebra, on the big sigma algebra, right? Well, there are lots of questions, that you ask yourselves. What if the measure is given to be countably additive or merely finitely additive? And then whether it is invariant under a certain group of transformations, right? Under rigid motions, let's say, under translations, under affine maps. So a whole lot of issues comes into the picture. Be the stumbling block in pushing the classical Lebesgue measure from the sigma algebra of measurable sets to the entire power set. It plays foul. This is the spoiler in chief, as we call it. It doesn't let it happen. And then when you try to do the same thing in an infinite dimensional setting, infinite dimensional space setting, the range of the measure is not the real line or the positive reals, but an entire Banach space, an infinite dimensional Banach space at that. What happens? So there the need arises to look for a choice-independent proof of the existence of non-measurable sets. So this is the main motivation. And it's so interesting that there are proofs of which I didn't know earlier. I stumbled upon these much later when I was looking at these issues. It turns out that you can produce examples of non-measurable sets of reals, very concrete world of reals. But then you have to invoke techniques from here and there, all of mathematics, harmonic analysis, finite groups, which Professor Bala was talking about, and groups of rigid motions and stuff like that. I'm going to demonstrate that in a moment how complicated life can be without choice, without extra choice. You see, during my graduate years, while I was at Kanpur, it turned out that people had written many papers on which were titled "Life Without T2." I still have 2 papers of your "Life Without T2." So it was really interesting. T2 is Hausdorff property. So that is what motivated me to title my talk "Life Without Choice." So it has been a very pesky issue, very irritating throughout the history of mathematics. ZF plus, it's mentioned in books and papers. If you prove a theorem, then you write in brackets ZF plus AC. Or if you don't use AC, then you don't need to write ZF. ZF means the Zermelo-Fraenkel system of actions, 5 of them, plus action of choice. And then what Gödel did about, or Paul Cohen did about action of choice, there's a separate story. So it has generated a lot of heat and dust over scores of years. There are big people around who still are skeptic about the action of choice. Well, my personal feeling is that trying to do mathematics without choice is something, you are living your life without earning a penny, without having anything to eat in the evening. You can't live a life without the proper resources. Like you can't do mathematics in its fruitful and successful sense if you discard the action of choice. You see, such big names as Roger Penrose says that I'm skeptic about it. I'm inclined to believe that it's not true. So
But you are saying that you can show the existence of non-measurable set without using.
without using action.
But
I mean, what does that mean without using action? I mean, that is what we have to understand. This means action of choice, for example, it leads to a result P. So P is weaker than AC. I'm using that P. And P is known to be weaker. It's known to be. There's a proof that P is weaker than AC. So that kind of a thing. So AC does come in. Action of choice does not need the certificate of an nincompoop, of an ant, of a cockroach like me. But then what I'm going to talk about is that action of choice is there to stay, and it ought to. Otherwise, our real life and our mathematical lives would get that much more difficult. So that's it. Do we have the pointer? Achha, achha, achha.
Arrow.
All right. So, how do we do it in the beginning? How do we do it? We use axiom of choice to prove the non-measurable set. How do we do it? Well, the Vitalis construction. Everybody knows it. Is supposed to know. I'll be surprised if one didn't know about it. In any case, I will come to that later. So I have saved it for myself according to Russell Paulus maxim. You have to give at least one proof. I will settle for that, one line proof. So the joke is that you can't call it a proof, it's so simple. So I'm combining both these. All right. Well, this is Vitalis proof and too simple to repeat here. What do? We take the rationals in the unit interval, then define an equivalence relation between two numbers if their difference is irrational, and then we have partition sets. This one, M alpha. Every equivalence class partitions the given set into disjoint classes, right? And then I use axiom of choice to pick one member from each. That's allowed. The rest is all simple. The representatives of those classes. Nothing would get simpler than this. Now you also want this Lebesgue measure. I mean, it's translation invariant. In fact, it's invariant under rotations as well, as we know. And this is unique. This is unique as a countably additive translation invariant measure on the sigma algebra of all measurable sets. So the Lebesgue measure of the unit interval is 1, and by this it's 0, monotonic. Therefore, this is less than this. Some, since it's countably additive, it will go in, and then since it's translation invariant, it will be this. And A is contained, all of this is contained in this 0, 2, you will get 2. Of course, 1 is less than 2, so there's no contradiction. But here, what is the contradiction? You get simultaneously, this is an infinite sum of non-negative reals. This would blow up unless it is 0. But it can't be 0 because it's strictly greater than strictly greater than 1.
Yeah, one is less than or equal to say.
Yeah, 1 is lesser. Yeah, okay, it's not lesser equals okay, but 1 is less than 0. So it's absurd. So simple a proof. So why go to all of that? I will just indicate, the irreducible minimum of the technical details that we need to prove the existence of a non-measurable set without axiom of choice. So that is all I'm going to do. Or you can call it quits. You can say, ठीक है, बहुत complicated होगा, बैठ जाइए. So that's one way for you to be done with this. Well, there are many solutions. There are many proofs of the existence of non-measurable sets using axiom of choice. That was direct. This is indirect. You take this functional equation. What are its solutions for reals? Of course, the identity function or a scale multiple, CX, right? So those are the solutions, but are there any other? Well, if you just assume they are additive, these are homomorphisms, group homomorphisms are. If you assume it is continuous just at one point, then it will be continuous how? Because of additivity. And therefore, the only continuous solutions are the CXs. However, there are discontinuous solutions of this function as well. And those discontinuous solutions of this turn out to be a consequence of the action of choice, and they turn out to be non-measurable. Those solutions are non-measurable functions, and that will lead to the existence of a non-measurable set of reals, right? And how does the action of choice come into play? By the very first line of the proof, choose a Hamel basis. So once you are given a Hamel basis, the rest is all okay, These guys, these reals, they give rise to linear functionals. In fact, additive functions, which are exactly these, and this is what it is. I mean, it's too trivial for me to repeat the details. You can see this. This is another. Should I repeat? Should I explain the details? These are simple. And then there is another proof. I'm not going to give you the details of. This is. Oh, that. What happens if I take continuous? Then multiples of x are the only solutions. If it is not continuous, then you get that kind of a solution, which I explained, which I showed in the last slide, right? Now, is there something between these two, continuous and non-measurable? Well, it turns out again that if you have an additive function, f of x plus y is f of x plus f of y, and if it is Lebesgue measurable, then it's automatically continuous. It turns out by Steinhaus theorem. How many of you have heard of that? If A is a measurable set with possible Lebesgue measure, then its difference contains an interval about the origin. So that's used here. I think number theorists are also using that somewhere. Okay. So
This one. Again, directly that minus alpha is a set of f inverse of minus L, and again minus
yeah, because this is
KP.
this is measurable.
And what would
This interval, open interval. So this is a measurable set of positive
I
measure.
mean, what are you saying that both the terms are the
Both
same?
the terms are the same.
It's some typo or something.
This one and this one.
Yeah.
Oh, they are the same. A minus A. These are sets.
Set.
So it's a set. It's a difference of two sets.
Okay.
So therefore it will contain the origin. And therefore it will contain an interval like this. So these are not reals. So this is the difference of. So you were talking about that set A plus B.
A minus B. Yeah.
Yeah, this is that. Okay. So you get. Let's postpone the nitty-gritty of the details of the proof. Very minor details, though. There is also a proof using graph theory, right? Some properties of bipartite graphs and a characterization of certain kinds of graphs, right? Which are cyclic. So that's used there. Naturally, I have no choice but to ignore that. In fact, I have deleted it from here because of paucity of time. And here it is. Non-measurable sets by other means. So where nothing like action of choice or its relative are used. So we have to use some group theory, the orthogonal group, special orthogonal group, and these are the familiar symbols for the Euclidean space of dimension n, and then the unit sphere, unit bond, and all that. And then you know what a group action is. You are given a group, And the set group action is nothing but a map from G cross X to X with those properties, right? The familiar properties. Huh? नहीं नहीं इन्होंने साहब यहाँ इन्होंने गड़बड़ करी हाँ? आपकी वॉच गलत है There's, huh?
5 plus 5 if you want that. So 5, 30 plus 5. So for 30 this
So, no, I thought I'll finish by 4.
Yeah, so what he is saying is that for 30 minutes it is 5, so afterwards 5 or 5.
you have 10 maximum.
So I have 10 minutes.
With no questions.
अच्छा अच्छा they can throw in questions during the talk. So so this is the group action. It is said to be free if what's this?
Sometimes it's a case so that can happen only for the ego time.
Yes, only for the acting. Is there something missing?
No, it's right, I think. Yes. The GFX equal to X. That's all. That's fine.
Ah, yes, it's GX.
GFX equal to X.
Postfix, right? And this is used basically, and its various equivalent formulations. And various equivalent formulations. And a very startling consequence, yet another startling consequence of the action of choice is the Banach-Tarski paradox, as you all know. So you have a ball, a cricket ball, or an apple. You can break it into finitely many parts, 5 to be precise, and then you can reassemble them, kind of juggle around them and get 2 balls the same size. Jadugari, literally. So this was a paradox. Still, we had a proof. Once there's a proof of something which looks non-intuitive, so it's called a paradox. So it no longer is a paradox, but the terminology is still there, Banach-Tarski paradox. So this is it. Now, why does it happen? Again, because of the action of choice. And it turns out that the unit sphere in R3 is paradoxical. This SO3 paradoxical means that you can divide the football. You can talk about, think about. S2 is the surface of a sphere, so which means a football, volleyball. And what happens? You can break it into a few parts and then reassemble them. Means subject them to isometries coming from SO3, special orthogonal group, 3x3 matrices, right? They what does a map do? It takes an object to some other object, and its shape may look different. Distance are the same; these are isometries. But then its geometry can change and does change here. It changes so much that apparently it looks like the volumes have doubled in the process. So this is paradoxical, this set. And it is this that will be seen later through a whole lot of steps to lead to the existence of a non-measurable set. So we need free groups on 2 generators, right? Whatever that means, not the time here to talk about. This free group on 2 generators turns out to be paradoxical in the same sense in which I have described it. You can break it into certain parts. You can take a partition, mathematically speaking. This F2 is paradoxical with respect to its own action, F2 acting on itself by multiplication, right? And then this special orthogonal group that contains F2, the free group on 2 generators as a subgroup, and by virtue of another theorem making use of the axiom of choice, SO3 itself would be paradoxical, and that's what corollary 2-3 is all about. And finally, we use Hahn-Banach theorem at some stage to get non-measurable sets. This is the nitty-gritty of the proof. Unfortunately, I have to give it a miss. Can't do better than this. But one last thing that I would like to say is the following. You see, Action of choice is irritating because it leads to the something like the Banach-Tarski paradox, as well as non-measurable sets and such like, monstrosities. The question is, will the world be much better in case we discarded action of choice for all times to come? Mathematics would be that much poorer, but what would we get in the process if we discarded it? Of course, we will have lost a very important part of our arsenal to prove theorems in mathematics. That's what mathematicians do, number one. Secondly, if we stuck only to Zermelo-Fraenkel, do we get, in the absence of action of choice, something like the Banach-Tarski or the non-measurable set? The answer is yes. Even more startling consequences than Banach-Tarski. So therefore, action of choice kahin jaane ka nahi. It has to stay there. Because in its absence, you get even more irritating consequences. And here is one. You take the reals and quotient it out by rationals. Cardinality is strictly bigger than this. कभी सुना है आपने? You have a tournament. There are, say, 10 teams participating, and every team has a captain. They are more numerous than the number of players taking part in the tournament. So that is a consequence of Zeta without action of choice. So what is the conclusion? Action of choice is there to stay and ought to stay.
Is it real?
My father is really in a dressing room, always, always, the coach is always having a pleasure to have that kind of player who is fully committed and doing everything for the team. Like, absolutely committed.
What's going on? Okay, I think I must stop here. Thank you. Except that I will show you this picture. There are about these 10, 12, in fact 15 implications based on action of choice. And there is this implication diagram implies what? So for example, look at the middle line. It is the Tishnov product theorem. Then
Followed your domestic seasons. You've witnessed outstanding well. You deserve to be here. So very enjoyable.
so these are various
That moment, I still
implications.
remember coming from someone like you coming. Okay, I didn't think that this is coming up to me or what compared to what you guys had back in your days and fighting family pressure,
Online join na.
pressure, financial issues.
So that's another thing is happening.
How do you manage to actually create a career?
So you are being told leave the numbers, listen to that.
I wanted to play any kind of sport. Don't want to go to the school. I want to play any school. So
Yeah, actually, I mean, yeah, sorry. Yeah. I mean, axiom of choice is a very intuitively acceptable concept. I mean, not such a demon.
But why did people begin to suspect it from day one? There was something wrong. The consequences that followed from it were really worrying. On the face of it, there's but then this is only about the finite number.
That is important.
About different
In fact, choice of axioms should be as minimum as possible.
Mm.
Finitely, when
Yeah.
the public being means
No, but I mean, Roger Penrose continues to be skeptical about it. So that is surprising. Well,
I think we'll have to stop.
Yeah.
Thank you. Very enlightening.
it was 10% of what I should talk about. Like you.
You should be like that. You should have that kind of base. At one moment you were from the middle.
I have no choice.
Yeah.
मेरे ऊपर भी बॉस है तुझे रोकना
क्योंकि
पड़ा
अभी उनका टारगेट
नहीं, मेरे केस हुआ है वो अपना अपना मुझे वो करेंगे खींचेंगे नेक्स्ट कौन है we now have the next speaker, Mr. Gopal Dutt.
मार्टल को भिजवा दिया
Will be position operators on deliver exponent in the big spaces.
construction
30 plus 5, 30 maximum. If you can,
But being the youngest speaker of the day, the small kids should be given little bit more. So, and you know, sir, how difficult task it is to speak after Professor, the first speaker of the day, Professor Govindam, Professor Ravinda, Professor Sophie, and then there's a big heavy burden. So that's why so thanks to the organizer for giving the opportunity to be here and to have an interaction session with the people to whom actually we learn. So the topic today is composition operator on the variant exponential basis. My job has been done little easy by Professor Sophie because the thing started from elementary from Subramaniam Ji, and then the flight of lectures has taken off by Professor Sophie on miserable spaces and all that.
That's what we used to say in MSc.
So from that all, now the flight has got to be on this smooth track, and I will be going with this topic. And one good thing is that, but now the term visa has come up over here. And another thing today, the first lifetime achievement award by the BJP is given to Professor R.K. Singh. And this topic basically composition operator. If you see, this entire domain flourished in India by the efforts of Professor R.K. Singh. And Professor R.K. Singh was student of Professor Nordgren, who was basically the mathematician who just put up this notion into this course. First, the systematic study of composition operator came by Nordgren in 1968. And then Schwarz, Riss,
He was senior to Shapiro.
but the student Schwarz and Riss were the initial two students of Professor Nordgren, who did their work on the composition operator, and then this R.K. Singh was the third student. And in 72, he completed his PhD. So the talk, I will just go on these two parts. Basically, one thing is that I will go with the composition operator, and secondly, I will just go with the brief introduction of the variant exponent Lebesgue spaces, and the rest thing is to the all the research scholars, because the initial work that has been started on this is just in the 2024. So there is a lot of things that can be carried over from the well-known established Lebesgue spaces to the variant exponent Lebesgue spaces. And in a very brief way, what are these? In a simple form, in Lebesgue space, when you see that you just talk of the integration of the PS power of the functions, mod f to the power p should be. And the question is now, can instead of this p as a scalar, as constant, can we replace this p by some kind of functions? Instead of power p, it will be px. And then what kind of p has to be there? So we take a specific kind of p, some measurable functions with a specific kind of range, and those p are known as the variant. And now the question is now, and why such kind of spaces are very interesting? I will come. So first, I just go with a brief definition of what the composition operator, and then so. It's a hangover here. It's not moving, so it's hanged over.
आपका टेक्निकल असिस्टेंट
It's not working.
No.
Are you arrow? You are speaking arrow?
Yeah, arrow, but it's hang. The arrow is also. ये एक सेकंड सर ये टाइम जरा सा एक्सक्लूड कर दीजिएगा ये कहाँ से ये मूव कर रहे हैं सो
I am a human being, not a computer. This is time extend हो गया है.
अच्छा ठीक है सर so if I start with two normative set x and y and my fxc is the class of functions from x to e valued and this e is supposed to be the field and particularly we talk of the real or complex value and then we just talk of the start with a function u which is a scalar mapping means the e valued mapping at the moment from x to c and then question is if you start with any function which is from x to e and because e has a field structure so I can talk of the u dot f where it is a pointwise multiplication so the question is corresponding to f each f in fxe the function from x to e is my u dot f the pointwise multiplication function again comes out in that class and if it comes then we say that this f goes to u dot f is a mapping and if this fxe consists of a topological structure, I can talk of the continuity of this structure, and then we say this f goes to uf, it induces a bonded operator, and we denote it by mu. So if you have a u, then you can talk of mu. Now the question is whether this mu will be continuous or not. That's the question. And for which kind of u, you can talk of the continuity of this mu. And then this fxe are replaced by very different kind of collections. And the initial, the pupil started on the classical Lebesgue spaces, the LP spaces, which are very well used. And well used because of wonderful thing, because of their immediate connection with the differentiability and differential functions and all that, because they constitute the basis for these spaces. And that's why they easily connected with the solutions of differential equations, the Hermite, Lysander, and all that. They come as a solution for these spaces. So now similarly, if I take a mapping T from Y to X, and then this mapping is such that if I have a F from X to E, say function from X to E, then if my F composite T, I can talk of F composite T, it will be mapping from Y to E now, if my T is this. So if it comes as a function within the space, then this we find as a function. But the question is again, if you have a topological structure over these fxe and fye, then whether this mapping will be continuous or not. And if it comes out to be continuous mapping, we say that this is a composition operator induced by T. And then the question is, what kind of T will we have so that this one thing is now this function should be well defined. Well defined in the sense that F composite T should come out in the space fye. This should be. And the second one is this continuity. So because of the linear structures, we'll have the continuity. We can talk of the topological continuity is not trivial. So for what kind of T? Then this is what I was talking about. If you see the systematic study of this class of composition operator, earlier these classes appear in the work of Koopman when he was studying the problem of mechanics. But that time these operators not came in terms of the operator theoretic and algebraic structure, that was coming in terms of the simple functions and that's the linearity, non-linearity, that was not yet discussed and that's why. But the systematic format of the composition operator came in the work of Nordgren in 1968. And then Swartz and Riz, they produced the initial two theses on the composition operator in the 69 and in 72. Singh wrote his PhD thesis on the composition operator under the supervision of Nordgren, and in 72 it was.
It's not Laura, it's Jack.
H.J. Schwartz.
Swartz. That's it.
You are confused. The Schwartz was Laurent Schwartz. That's
Oh, no. This is I'm not talking. It is H.D. Swartz. And then after this, I think if I'm not wrong, There are more than 100 PhD has been done on this direction. And a big lot of people from the Jammu, they have come across to work on composition operator on the different directions, on different spaces. And then, and by lot of work has been done on the L2 spaces, because L2 spaces are some, because of some beautiful structures and all that. And then, what I'm just coming, because I assume that LP spaces are very well known to all of us, because most of the in post-graduation we go through that. It is class of, but in LP spaces, the functions are basically, they are representative of the equivalence classes. And those, the functions which comes over here, they are equal almost everywhere. In that way they are correct. So these are the functions. So here now again, so here if I start with a sigma finite meter space, my piece is taken as to be a this mapping from X to 1, take it out. We have a meter, and so we can have the meter infinite. Infinity function, variable functions, then this function we call as variable function, this variable exponent. And corresponding to this P, we talk of this space, this collection of those visible functions for which this power is Px. It is just a generalization of LP spaces. And in LP spaces also, if you just take it to place that Px equals P, it comes out to be the LP space. And then this comes out to be finite for some lambda, then we can, this Luxembourg norm, which comes out to, it's again the fault of the AI. Somebody told that it is the AI.
Yeah.
So,
Don't go too close.
so how to फिर से वहीं पर यहीं पर टच करना मतलब यहीं पर people I think it's visible still. So even if I take this collection, serious about touching it. So if this is by Luxembourg norm, then it comes out with norm and the space becomes a Banach space with respect to this norm. And these are some notions I will use. Essentially, and essential.
The AI is already in motion there, yeah.
And then
It would be a causal norm, because Px is not linear or sub-linear.
it's a quasi norm, but it will complete in sense I might Banach, it will come to Banach quasi.
But if you have a quasi norm, if you complete it, it would still be
Yeah,
a quasi Banach. Quasi.
With quasi Banach.
No.
Quasi. In beginners, the Banach space completeness is more important for me. And in some generalization, when you come from this to, there is another generalization of LP spaces, is Laurent spaces. When we come from one indices to two indices.
These are non.
So in that case, this quasi norm comes out to equivalent to some norm. There's a replacement of equivalency of that, where it becomes the norm and equivalent to that. So usme you get the benefit with replacing equivalency will give you the transferring of result from one respect to one to another respect to another. But it becomes quasi norm here. So we call it in many spaces it becomes norm also, and then we name it Luxembourg norm. This notion. ये फिर से इसमें सर कुछ हैंग कर गया आपका यहाँ पे ये and then the question is now, the main question is now for me is that one classical result that came in the study of about the composition operator on this direction was what kind of P this CT from LP space to LP space is a well-defined mapping, and secondly when it will be continuous, that means bondedness of that CT also. And one thing is that there is a notion that is called non-singular. What is non-singular means? If suppose my T is a mapping, so this is something about a slide about variable Lebesgue spaces, and if you see the earliest appearance of this, it came in the work of the Orlik, but Orlik had so many papers, and even Orlik space, which came by in the work of the Orlik, and he has more paper. But there's only one paper of Orlik in which this notion appeared first. This variable space, the exponent Lebesgue spaces. And then that was the only paper basically initial literature, but in the last centuries, last decade, one book has been written by Alberto Fiorenza and some other author with his co-authors. Now, what is